Welcome to AP Calculus, Section 2.1, Day 1, which is kind of how I label the lessons and the recordings. This is the beginning of Chapter 2, which is our first chapter in calculus. And this chapter covers a myriad of things, mostly limits. We throw in some continuity, and we also have rates of change. Rates of change are really derivatives, the instantaneous rates of change at least, and we'll cover those in much more depth in Chapter 3, but they do throw in some different examples for this in this section. So we'll start out with a little bit of that, and what we're going to look at is the difference between average speed and instantaneous speed, and with an example of a rock breaking loose from the top of the cliff and falling. So we're going to find the average speed for the first 5 seconds of fall, and then we're going to find the instantaneous speed, which means the speed at an instant. So a general equation for speed or for distance equals rate times time. If we call our rate our average speed, that means that the rate is equal to the distance divided by time. We also sometimes write this as the change in y over the change in x. And, or we could use actually change in time, which might be better. Change in time. All right, that's if our y value is on the y-axis and our t value is on the x-axis. So we have a rock falling down, and we're going to use this equation, y equals 16t squared, and find the change in y over the change in time to give the average speed for the first 5 seconds. Well, the change in y is 16(5) squared minus 16(0) squared over the time at the end minus the time at the beginning. All right, so if we calculate that, we get 400 over 5, or 80. And we'll call that feet. Does it say it's feet? Feet per second. We're calling it feet. Okay. Next, we're going to find, using the same equation, that the speed at the instant t equals 5. Because the speed could be going, what was it, 80? It could be going 60 for a while, then 190, and then 80 for a while. So it could be going different speeds, and we want to know the exact speed at t equals 5. All right, so what we're going to do is really use the definition of a derivative, is what this turns out to be. And what we're going to do is find out the speed from t equals 5 up to t equals 5 plus h. H is a teeny, teeny, tiny bit larger or smaller than 5. So what we're going to do is pretend that it's a little bit larger, and we're going to take the change in y over the change in time. All right, so the change in y is going to be 16, 5 plus h squared minus 16 times 5 squared. And we're going to divide that by 5 plus h minus 5. And what we're really going to do is take the limit of this as the h gets smaller and smaller, which means the h going to 0. So we have to calculate this out, which means we're going to have to FOIL this 5 plus h. So we have 16, 25 plus 10 h's plus h squared. We have to multiply that all by 16. Minus 16 times 25 over 5 plus h minus 5. These cancel out, right? And we're left with an h. And if we simplify this one more time, this times, you can use a color pen, this times 16 and this times 16 cancel out. We're left with 16 times 10h plus h squared divided by h. And this is going to equal 160 60h's plus 16h squareds. If we divide both of those by an h, we're going to get, longer page, 160 plus 16 h's. And again, we're going to take the limit of this as the h goes to 0. When this h goes to 0, that term will go to 0, and we're left with 160, I think we called it feet per second. That's the instantaneous speed at t equals 5 compared with the average speed at t equals 5, from 0 to 5. So that's a little introduction of average speed versus instantaneous speed. It's one of the key concepts of calculus, because instantaneous speed, we will learn later, is the derivative, and that is the slope of a tangent line at a point. So that is speed.